Hello everyone, I'm Fanshu Meng from Peking University, the first author of PiSSA, a novel parameter-efficient fine-tuning method. Parameter-efficient fine-tuning, PEFT, aims to reduce the costs associated with the highly resource-intensive process of fine-tuning large models. LoRA, or low-rank adaptation, inserts two low-dimensional matrices, A and B, into the target linear layer. By freezing the original weights and only fine-tuning these newly added adapters, LoRA significantly reduces the number of trainable parameters. In our paper, we explore the initialization methods for LoRA and how they affect the gradient direction during training. Let's examine how LoRA initializes its adapters. The key principle is that the newly inserted modules should not disrupt the model's original capabilities. Therefore, LoRA initializes matrix A with Gaussian noise and matrix B with zeros. However, when we compute the gradients, we find that the initial gradient of A is 0, while B's initial gradient direction is random. This combination of 0 and random gradient directions can slow down LoRA's convergence speed and may lead to convergence at suboptimal local minima. In our approach, we decompose the original matrix W into a low-rank principal part and a residual long-tail part based on the magnitude of the singular values. The low-rank principal part comprises matrices A and B, which we initialize using the top R singular values and their corresponding singular vectors. The residual component is used to initialize W to preserve the model's overall functionality. By fine-tuning the principal part, the gradient directions of A and B are aligned with the principal components of the original matrix, leading to faster convergence and improved performance. To illustrate, let's consider a toy example. We train an MLP on the MNIST handwritten digit recognition task. Full fine-tuning red line, LoRA blue line, and PiSSA orange line. After the same number of iterations, marked by cross symbols, PiSSA converges to the target local minimum faster than LoRA. Beyond initialization, quantization is another key aspect of parameter-efficient fine-tuning. LoRA, a widely adopted method, has a structure very similar to LoRA but quantizes the base matrix using normal float-4 precision. The quantization error in LoRA can be expressed as the difference between the original matrix and the quantized matrix plus a multiple B. Since B is approximately 0, LoRA's quantization error is effectively the same as directly quantizing the original matrix. Similar to LoRA, our PiSSA uses NF4 precision to quantize the residual matrix. Since the principal singular values and vectors are stored in full precision in A and B, the residual matrix has a much smaller magnitude than the original matrix, resulting in reduced quantization error. Moreover, PiSSA removes outliers from the matrix, making its distribution closer to normal, which further minimizes quantization error. In this table, we apply PiSSA to the QKVO attention layers and gate up-down MLP layers of 3 large language models. We observe that PiSSA reduces quantization error by approximately 20%, outperforming LoFT-Q, a method specifically designed to reduce quantization error, and LoRA, which does not reduce quantization error. Beyond reducing quantization error, PiSSA's trainable parameters are initialized in the same way as PiSSA, leading to similarly fast convergence and strong performance. To evaluate our method, we first compared PiSSA with full fine-tuning across 3 models, Llama, Mistral, and Gemma, on tasks such as math, code generation, and conversational generation. We found that PiSSA outperformed LoRA and in many cases even surpassed full fine-tuning. Next, we compared PiSSA with other PEFT methods on the GLUE benchmark, showing an average improvement of about 1% over LoRA. We extended our experiments to additional models and observed that across a range of model sizes, from 7 to 70 billion parameters, and across both standard and mixture of experts models, PiSSA consistently outperformed LoRA. We also conducted experiments at different ranks. Both PiSSA and PiSSA consistently achieved better quantization error reduction, lower training loss, and higher test accuracy than other methods. In conclusion, we introduced the principal singular values and vector initialization methods for low-rank adapters. This initialization enables efficient optimization performance, and PiSSA can be implemented with only minor modifications to the existing LoRA code. Our paper, code, and models are available at the following links. Thanks for listening.